An insulating sphere with the radius r has a uniform positive volume charge density of rho. Okay, so let's see, I'm going to write this out real quick. So I'm going to say that rho equals a small bit of charge for a small bit of volume. V there is volume, not voltage. Symbol is the same, so it's easy to get confused. Solid metallic shell with inner radius r and outer radius 2r, okay, has 0 total charge. Express your answers parts A through D using rho r for radius, and constants. What is the magnitude of the electric field at a distance r equals 3r away from the center? All right, so there are multiple ways of approaching this. The way I am going to look at this one is through Gauss's law. So Q net over epsilon naught equals electric flux, which will equal integral E dot dA. So to explain this a little bit, so Q net is the total charge, epsilon naught is a constant. This is the electric field. It is a vector, and one of the details about it that's important is when you draw electric field lines, it's assumed for a positive that you start at the positive and it points outward radially. Yes. And the area vector, say the area for whatever sphere, I'm going to use this sphere here as a thing to take the area of. The area vector will be perpendicular to the surface, which will make it parallel to electric field lines. So this dot right here, not just a dot, not a multiplication, but in fact a dot product. So dot product is a measure of how parallel two things are. You can think of it as the cosine of theta between the two angles. And since the two are parallel, that's just going to be 1. So it's going to be, you could think of it as multiplying it by the cosine of 0. Cosine of 0 is 1. And so we can rearrange this a little bit. Dot product of two vectors will give you a scalar. And so we can rewrite this as integral E dA, which, since the E, the electric field, since it radiates out radially, will be the same at every point on the surface of our imaginary sphere that we have here. So we can write this as E dA, where this right here is the area of the sphere. Rearranging things slightly, we get E equals, let's see here, Q net times, Q net divided by epsilon naught times integral, I'm going to write this just as area sphere. But really, I mean the integral of dA. All right, so this is our formula that we're going to use. Move this down here real quick. I know, running out of space. So for Q net, we know the electric charge density of our inner sphere, which is rho, and rho is for a small bit of volume. Therefore, Q total, which in this case is going to be Q net, is going to be the charge per unit volume times the total amount of volume. Volume of the sphere is 4/3 pi r cubed. And since our sphere is r big, the r is actually just going to be the big R. So we have rho times 4/3 pi r cubed all over epsilon naught times the area of the sphere that we're measuring this at. Now we're measuring it at r equals 3r. So this is 3r distance from here to there. So the area of a sphere is 4 pi r squared. But in this case, I'll make that little r. This little r right here is actually going to be 3r. And so we have 4 pi 3r squared, which gives us 4 pi 9r squared, because there's the quantity there. I know it sounds the same when I say it that way. I don't really pronounce the parentheses as much as I should. So then, writing this down, we have 4 pi 9r squared, and this is the electric field. Do some canceling with a color that offers better contrast. There we go, the 4 pi's. And we are left with rho R over 27, 3 times 9, epsilon naught. Yes, quite plausible. Very, very plausible. I'm going to say that is actually even the answer. The electric field, the magnitude, is rho times r times 27 epsilon naught at a distance of 3r. Yeah, I'm good with that. So then, on to the next part. Assuming the potential infinity is 0, what is the potential at the outer surface? R equals 2r of the metallic shell. All right, so I'm going to say we're going to try to find the potential at right that point, right there. So there's different ways of doing it. So the definition of potential is the energy required to bring a test charge from infinity, most likely, to whatever point you're trying to test potential for. Another definition that's going to be more useful in this case is voltage equals negative integral of E dot dr, or dl. It's a line integral. You know, you're right, I should use L. In this case, it's going to be the same as R, but you're right, L should be better. And we're going to go from negative infinity with potential at the outer surface to 2r. Okay? And we have our formula. Can I use this formula over here? Maybe I could. I'm not going to. I'm going to look at it in terms of the electric field will be, and we'll do the same idea. So we're going to use Q net over E epsilon naught. Yeah, pi r sphere squared, maybe. So for this case, I'm just going to use the formula for electric field of a point charge. We could derive it using the Gauss's law above, but this is pretty well known. So I'm going to call it KQ over r squared. So K, in this case, is 1 over 4 pi epsilon naught. And Q is going to be the charge of the inner sphere, which is going to be the volume, 4/3 pi r cubed, big R, times rho. And those are all going to be constants. So I'm going to rewrite this as, let's see here. So we pull this out, we're going to have K 4/3 pi r cubed times rho. And then I'm going to get rid of the negative by flipping the limits of integration. And we're left with this r squared, which I'm going to write as r to the negative second, dr. Yep, I'm good with that. Clean some of this off to give myself some space. I was able to factor these out, or pull these out of the integral because they are constants. And then we just have to take this integral right here. So we get K 4/3 pi r cubed rho r to the negative 1 over negative 1. Limits of integration. I'm going to flip them again, double flip, plus, and I'm going to rewrite this one more time just so we can see it more easily. 4/3 pi r cubed, put in a K. Nope, looks like a negative. Don't mean to have the negative there. K rho, and then we'll do 1 over 2r minus 1 over infinity. I know you're not supposed to write infinity in there, but we'll get the idea here. So 1 over infinity, that's just going to be 0. That's what they're talking about with we assume that potential at infinity is 0. And from here then, we can just solve this. V equals, we'll cancel the 2, we'll cancel an r, and we get 2/3 K pi r squared rho. Now it'll be the potential at 2r, at a distance of 2r on the outside of the conductor. So one thing to note here, though, is we're like, wow, how do we have a pi in there? I thought there'd be, no pi, because there's no pi in the electric field over here. There really isn't a pi involved here, because before I used epsilon naught, and this time I used k, and k equals 1 over 4 pi epsilon naught. And if you plugged this in for k, the pi's would cancel. So it's always good to be like, oh, I got a pi in this term, but I didn't have it in the previous one. It's good to understand why. but K involves a 1 over pi in it, so that's why you kind of pick up extra pi's, which I'm never going to object to extra pi, but from a mathematical point of view, you still want to be correct. What is the potential at the inner surface R equals 0 of the metallic shell? Okay, so the point here is inside a conductor, there is no electric potential always equals 0 inside an electric conductor. There's some nuance about why that is, but it's just good to know that inside a conductor, the electric potential is always 0. So for this one, it's going to be easy. Potential equals 0. Even draw some little things on top to make sure we know it's a capital V. What is the potential at the center of the insulating sphere? This one's a little bit different. Okay, so this one, I'm going to write this as, let's see, work equals Q times V. One of the ways to know that is work is measured in energy, is a measure of energy. One of the units of energy is an electron volt, so electron, Q, V, volts. And we also know that work equals F dot dr. So one of the definitions of voltage is the amount of work required to bring a test charge from infinity, that's going to be our test charge Q, and to a given point. This given point that we're using now is R equals 0 in the middle of the sphere. So force, in this case, is going to be due to an electric force, which is going to be K Q over, I think it's K1, K2. Yeah, I'm going to say K1, K2 over R squared. I'll call this one Q1. I mean Q, not K. R squared. So I'm going to rewrite this as Q1, factor out the K. This would leave the Q2 over here. R squared dr. Same idea. Did I forget anything? Nope, I think I'm good. Maybe. Think so. I'll leave the K in here. Okay, there we go. So we have this set of equalities here. And then I'm going to look at just this part here, that part here, and we're going to go from infinity to 0. So this might look similar to the formula we had up here about V equals negative integral e to the dot dl. So, which is true. So we basically just derived that. But from an intuitive sense, we're like, well, this helps me. So we're also going to break this up into various parts here. So I'm going to start by going from infinity to 2r, because that'll all be the same kind of idea here. And this will be k q r to the negative second dr. We just kind of did that equation. Well, I think we could probably even use that right here. Yes, I think we can. And then we're going to add to that kq from 2r to 1r dr. I'll leave the negative. Can I do this? I'll say this. No, that's not true. I'm just going to say something like 2r. Nah, I'm going to be even more general. The potential from 2 to 1, 2r to 1r, plus r to 0, and this would be do something along the lines of I'm going to factor out the k, but I'm going to leave this q in here because that's going to change as we go through the insulator, times r to the negative second dr. So over here I factored it because when we're outside of the inner insulating sphere, the total charge is going to stay constant. But when we're actually moving through the inner insulating sphere, as we move through it, the amount of charge interior, Q net, is going to decrease. So I couldn't factor it out here. And then going through this and simplifying it a little bit, we know that the voltage inside a conductor, this conductor up here, is going to be 0. So we can just say that part, 0. So for this part, we already solved that, and we got 2/3 k pi r squared times rho. And now we need to solve this portion right here. So q equals 4/3 pi r cubed. And then we're going to multiply that by, or divide that by r squared. And we're taking the integral of that. Go to that q real quick. dr. So one of the bottom r squared will cancel, and we're left with an r on top. And this will be 4/3 pi. I think there's supposed to be a rho in here as well. We'll leave it, put a rho in there. 4/3 pi r, 4/3 pi rho r squared over 2, because the integral of r will be r squared over 2. And this will be evaluated from r to 0. Yeah, that seems reasonable. I think there's supposed to be a negative involved. I think I forgot the negative. That's okay. I'll put it in a sec. So 2 and the 4 will cancel a little bit there. And we're left with 2/3 pi rho r r squared. So this will be 0 minus r squared. So I'm going to put in the negative there to kind of flip it. I know, terrible boardsmanship, but it is what it is. 2/3 pi rho r squared. Yep, I think that's the answer to that part. So then we're going to add on 2/3 pi rho r squared. I think there's supposed to also be a k. Did I forget the k? I'll put in a k. There we go. I know, very haphazard. So we have 2/3 pi. Wait a sec, is this just double? That feels suspicious. Seems right. I'm going to kind of go with this. But yeah, suspicious. So since these are exactly the same, I can just add them together and I get 4/3 pi r squared k times rho. Interesting. Interesting. Suspicious. Okay, so that's what I would say would be the electric potential at the center of the insulating sphere. Okay, then the last question. If a metallic shell is replaced with an insulating shell with inner radius r, outer radius 2r, has no charge anywhere, the insulating core remains the same, circle which one, or ones, of the previous questions will have a different answer. Okay, so the only point where the insulator played a role was part C. So at part C, that was when we were inside the conductor, and inside a conductor you have 0 electric potential. So C would be the only one that was different. A was we stayed outside of both, so that would be fine. B, we still stayed outside of both spheres, so that's good too. C we talked about. And then for D, the electric potential wouldn't change because since we passed through both the outer and the inner, the electric potential required would be the same because one would cancel each other out. One would cancel out the other. So C would change, the others would be the same. Okay, sounds good. I'm going to move on to I think there's an F here. Two long parallel conductors are a distance 4r apart, center to center. A thin-walled cylindrical shell with its center at x equals 0 has radius r and carries a current of 3I in the z direction, where z is out of the page. Wire at x equals 4, that one right there, carries a current I along the z direction. Okay, so they're all positive z. What is the magnitude of the electric field at x equals 2r? So your answer is using r, I, and constants. Okay, so this is a Biot-Savart law. You can use the Biot-Savart law to find the current, the magnetic field produced by current carrying wire. So long story short, mu naught I over 2 pi r. 2 pi r. And so it's going to follow the right-hand rule. So if we draw, we're looking at x equals 2r, so halfway between the two. So we have something kind of like this maybe. Click off to the side. Take our circle. A little bit thinner, a little bit thinner. Purple? Yep, definitely should be purple. And so if this is the magnetic field at 2R due to the cylinder, which you can approximate as a wire, and this is the one due to this one, let's see, a little bit thinner, a little bit thinner. Let's try and see where they overlap. Okay, not perfect, but we're going to call that good enough. So if you use the right-hand rule for this, wires coming out of the page, the magnetic field will be going this direction. So for this one, magnetic field is going out of the page, and you use your fingers, lay your thumb along the wire, wrap your fingers, and that will give you the direction of magnetic field. And you can see that in the middle here, they oppose each other. And so what we're going to do then is just add them. One will be negative of the other. So it'll be total, magnetic field total, will equal mu naught I. I'm going to call this 1, the other one 2. 1 over 2 pi R1 minus mu naught I2 over 2 pi R2. Now, since it's at 4 and we're looking at the middle of 2, the radiuses, or radii will be the same. I1, I think, is 3. And the other one is 1. So this will be mu naught 3I over 2 pi 2. 2 is the radius, minus mu naught I, single I, over 2 pi 2. Factoring things out and simplifying, we get something along the lines of mu naught 2I, 3 minus 1, over 2 pi 2. The 2's cancel, and we got mu naught I over 2 pi, magnetic field. And this is going to be dominated by the one on the left, so the magnetic field will be upward. And since it's a vector, we probably should say upward, upward. So we have a magnetic field going up. And they just asked for magnitude. So that's okay. I gave them direction as well. The big thing here is the two oppose each other. Find the coordinates of the location on the x-axis where the total magnetic field is 0. Okay, so it's the same idea here. What we're going to look here then is, so this is going to create magnetic field going up here due to 1, and then down on this side, like so. And if we look at the magnetic field of this wire, it's going to create magnetic field going down here. That's where they oppose. But then it's going to create upward over here and downward over here. So on this side over here and this side over here, the two wires actually reinforce each other. The only points where they oppose each other is in this region right here. And so we're going to have to find a region along here where the magnetic field is 0. And I'll do it right here. And so what we're going to do is Biot-Savart Law. So mu naught I1 over 2 pi r, but I'm going to call r x here. It's going to say this is the x-axis, equals mu naught I2 over 2 pi. And the way we're going to measure this radius will be 4 minus x. So within this area here, we can relate this radius here to x by saying 4 minus x. It's actually 4r minus x, I guess, is the correct way of phrasing it. So I should leave that in there. Okay. Going to simplify this just a little bit so we can know that mu naught, this can be 3i all over 2 pi x equals mu naught singular I all over 2 pi 4 minus x. Doing some canceling, the mu naughts will cancel, 2 pi's will cancel, the current will cancel, 4r minus x, always forget that r. So then we have 3 times 4r minus x equals, And I guess we're only left with x on this side, so x. So we have 12r minus 3x equals x. Moving the 3 over to the other side, we have 12r equals 4x. So we have 3r equals x. That can't be right. That's terrible. Something went terribly wrong here. Oh no, it could be 3r. Yep, because we had total 4r there. Yep, I'm good with this. So the point where the magnetic fields are 0 is closer to the weaker current. So it makes sense. So the point, find the location on the x-axis where the total magnetic field is 0. Express your answers in times, r, I, and constant. So x equals 3r. No, not too bad. 3/4 of the way across from one to the other. So that's how I do this problem. Hope that helped. See you next time.